Hi all. Let's see the next topic of Unit 3, floating point division. So in today's lecture, we are going to discuss about an introduction to floating point division and what are the steps of floating point division algorithm with the help of a flowchart. So coming to the introduction, a floating point division algorithm, it requires the exponents of a floating point numbers that has to be divided. Those exponent has to be subtracted and the mantissa part of the floating point numbers has to be divided. So for dividing the mantissa part of your floating point numbers, we are using a fixed point division algorithm or a sign magnitude division algorithm. The division algorithm of a floating point can be subdivided into 5 parts. The steps. There are 5 steps. The first step is to check for zeros. The second one is initialize the resistors and evaluate the sign. And the third step is align the dividend. And the fourth one is to subtract the exponents. And finally, divide the mantissa. So these are the 5 steps involved in a floating point division algorithm. Let us see each step in detail. So this is the flowchart of a floating point division. So we'll discuss this later after we cover the steps so that you will understand it better. So coming to the first step, check for zeros. So in the similar to your multiplication algorithm, here also we are going to check if any of the operands involved in the division algorithm is a zero. So as we know, the division algorithm contains 2 operands. One is AC and one is BR. So AC is going to store your dividend, whereas your BR register is going to store your divisor. So these 2 operands are checked for zeros. If BR is equal to 0, the divisor is equals to 0, then it is considered as a divide by 0 error. So we are going to attempt to divide a number by 0, which is an illegal operation. So this particular operation is going to be terminated with an error message. The next step, we are going to check if AC is equal to 0. AC means the dividend. If the dividend is equal to 0, then obviously if you 0 by something, if you divide, it becomes the result as 0. So your quotient also becomes 0. So if the dividend is a 0, the result, which is nothing but your quotient, which is stored in the register QR, it is set to 0. So you are not going to check for anything. You are going to check just the content of your AC register. If it is a 0, then you are going to set the quotient in a QR register to 0 and stop the operation. But if both AC and BR registers are not equal to 0, they contain some non-zero values, then we will proceed with the next step. So the first step in a division algorithm is to check for zeros, where you are going to check if any of your operands are a 0. Based on that, your result will vary. So if both the operands contains a non-zero values, we are going to proceed with the step 2. In step 2, you are going to initialize the registers and evaluate the sign of your quotient. So in this step, you have to initialize some of the registers that are used in the algorithm, and you have to also evaluate the sign of your quotient. So you need to determine the sign of the quotient and store that particular sign into a flip-flop of your quotient, which is QS flip-flop. So, how do you calculate the sign of your quotient? Is performing an XOR operation on the sign of the dividend, which is stored in AS, and the sign of the divisor, which is stored in a QS. So, QS stores your divisor, QS stores the sign of your divisor, and AS stores the sign bit of your dividend. So, you have to perform an XOR operation. So, this is not plus, this is actually an XOR operation. Okay. So, if your dividend and divisor both are either plus or both are either minus, then if you perform an XOR operation of 0 XOR 0 or 1 XOR 1, that gives you a result of 0, which means the quotient will become positive. If any of your divisor or a dividend contains a negative value, then obviously when you perform 0 XOR 1 or 1 XOR 0, then the quotient becomes 1. So you get a negative quotient. The sign bit of your quotient will be a negative, which is a 1. If both the signs are same, either plus or minus, dividend and divisor, then You get your quotient also as a positive. If any of your sign bits of a dividend or a divisor are a 1, then obviously the sign of your quotient becomes 1, which is a negative value. So the sign is a negative. So the sign of the dividend in AS is left unchanged to be the sign of the remainder. But for the remainder part of your division operation, whatever is the sign bit of your AS, that will be the sign of your remainder. The sign bit of the quotient depends upon the sign bits of AS and BS. The Q register. Next, you have to initialize some of the registers. The Q register is clear to all zeros. Initially, whatever is the content of Q register is initialized to all zeros, and the sequence counter is set to a number which is equal to the number of bits of your quotient. So n minus 1. So apart from your sign bit, you are not going to consider the sign bit into account. Other than the sign bit, the number of bits of your quotient determines the sequence counter, is initialized to a sequence counter. So that's why we are representing as sequence counter initialized to n minus 1. So if you are representing n, you are including a sign bit, where since you are not representing the sign bit, you are not taking a sign bit into account, you are representing a sequence counter as n minus 1. Next step of your division algorithm is aligning the dividend. So in aligning the dividend alignment is similar to how you check your divide overflow condition in case of a fixed point division algorithm. When we discussed about a sign magnitude or a fixed point division algorithm, we have come across something called as a divide overflow. So what do you mean by a divide overflow? So the division operation may result in a quotient with an overflow. So, what do you mean by a quotient with an overflow? Means the quotient is actually stored in a register, the standard register, which is of certain size, say 5-bit register. But after, say, if there is a situation that after performing a division operation, if your quotient cannot fit into a 5-bit register, if you require one more extra bit store your quotient, if your quotient becomes 6 bits, then we consider that as a divide overflow situation. So, in case of a division operation, before performing a division, we have to check if there is an overflow situation or not. So, in order to check the overflow situation, we have to subtract the divisor from the dividend. Okay. If the divisor, how this particular overflow situation will be identified is, if the divisor, if the dividend is less than the divisor, then we say that there is no overflow situation. If the dividend is greater than or equal to the divisor, then we say that there is a overflow situation in the division algorithm. So in order to determine if there is an overflow situation or not, we just subtract the divisor from the dividend. So we subtract the divisor from the dividend. See, we have already done this step in the sign magnitude division, and we have checked if there is a device overflow situation. We skip the magnitude division of your magnitude part. Similarly, here also we are going to check uh, the overflow situation by subtracting the divisor from the dividend. So after subtracting the divisor from the dividend, we are going to check the carry in EBIT. The result of the division subtraction operation will be stored in EA, where E stores your carry bit. So the carry in E flip-flop, it determines the magnitude, the relative magnitude, whether it is less than A is less than B or A is greater than or equal to B. That is determined based on the carry which is stored in the E flip-flop. If your carry is equal to 0 after performing a subtraction operation, then we mean to say that there is no overflow, which means A is less than B. When A is less than B, there is no overflow situation, which means your dividend is less than the divisor. A stores your dividend and B stores your divisor. Then you have to restore your dividend, because in order to check this overflow situation, you have subtracted the dividend from the divisor. So you have to restore your dividend back by adding the divisor back to the dividend. So you have to restore it after checking the condition. Similarly, if carry E is equal to 1, it means that there is an overflow situation. There is a divide overflow situation, which means this condition is satisfied. A might be greater than B or A might be equal to B. Any of this condition is satisfied. So whenever there is a uh, overflow situation in a division algorithm, In case of a floating point division, you have to align the dividend in such a way that there is no overflow situation. So how do you align the dividend is we have to perform a shift right operation on the contents of A and increment the dividend exponent. So the A stores the dividend. So you have to perform shift right one shift right operation on the contents of A, the dividend, and you have to increment the exponent of the dividend by 1. So since the both, so that your dividend will be aligned, and this alignment ensures that A is less than B, so it satisfies no overflow situation. So then after performing the shift right operation, after aligning your dividend, you have to restore the dividend by adding the divisor to the dividend. So you get your original dividend stored in your A register. Okay. So the dividend fraction is restored to its original value by adding the divisor. So this is how you align the dividend. So in this step, we are going to check if there is a divide overflow situation by subtracting the divisor from the dividend. Based on the subtraction operation, if the carry bit in a E flip-flop, if it contains a 0, we mean to say that there is no overflow, which means A is less than B. The situation is satisfied. If the carry flip-flop contains a value of 1, it means that there is an overflow situation. So whenever there is an overflow situation, normally in a sign magnitude division, we skip the dividing the mantissa part of your data. But in case of a floating point division, we are going to align a dividend in such a way that overflow situation is resolved. You have to perform a shift right on the contents of the dividend and increment the dividend exponent by 1. So that this alignment ensures that A less than B condition, which means no overflow situation, occurs. And then you are going to restore your dividend. How you are going to restore your dividend? By adding the divisor back to the dividend. So A contains your actual dividend now. So this is the alignment of dividend. So once the alignment of dividend is done, the next step is to subtract the exponents. So your exponents now are in the form of a power m by a power n. Means because you are performing a division operation. So when your exponents are the form of a power m by a power n, you have to perform a to the power of m minus n. No. So next the divisor exponent is subtracted from the dividend exponent. So whatever is the value of a power m minus n, that is your exponent of your quotient q. So the result is transferred into q because quotient is formed in qr. So whatever is the small q, that will become the exponent of your quotient, which is stored in a qr register. The next step is the dividing the mantisas. Now till now we have done with checking for zeros. You are aligned your exponent, you have subtracted your exponents, you have aligned your dividend such a way that there is no divide overflow situation. So the next step and the final step of your division operation is dividing the mantissa part of your data. So the magnitudes of the mantisas are divided based on the fixed point division algorithm. So this is similar to how you perform a sign magnitude division algorithm. You have to follow the same flowchart of sign magnitude division, and after the division operation is over, according to the sign magnitude flowchart, the mantissa quotient resides in the Q register, capital Q register, and the remainder resides in the capital A register, according to a sign magnitude division. So this is your this is the sign magnitude division flowchart. You need not have to check for this overflow or underflow situation because we have already checked the divide overflow and we have aligned our dividend. Now, only thing you have to do is divide the mantissa part using this part of your flowchart. So once it is done, your quotient will remain in a capital Q register and your remainder will remain in capital A register. Okay. So according to our flowchart, the floating point quotient, which is in Q, it resides in QR register because whatever is in capital Q, according to this particular flowchart, floating point flowchart, capital Q, whatever is the quotient, that is transferred into QR. So these are the steps of floating point division, where the first step we are going to check for zeros. So both your operands BR and AC are checked for zeros. If your divisor is a 0, you throw an error of divide by 0 error. If your dividend is a 0, then your quotient is set to 0. So, and you end the process. If both BR and AC contains a non-zero values, then next step is initialization of the registers, where you are going to initialize the sign bit of your quotient by performing AS XOR BS operation, where AS is the sign bit of your dividend and BS is the sign bit of your divisor. Next, you have to initialize the register capital Q to all zeros. And the sequence counter is set to n minus 1. The reason why I am giving n minus 1 is we are not including the sign bit. So n minus 1 represents the sequence counter is set to n minus 1, the number of bits of your quotient. Next, we are going to, the next step is aligning the dividend. So here we are going to check for a divide overflow situation. For that, you have to first subtract the divisor from the dividend. So a minus b. So that is done by a plus b complement plus 1. So this is a subtraction operation. After performing a subtraction operation, your result will be stored in EA. So you have to check the value in E flip-flop. If the value is 0, then it means there is no overflow situation. A is less than B. Your dividend is less than the divisor. In this case, you are just restoring the value. You have subtracted B to check if there is an overflow. So you have to restore the original value of A. For that, you are again adding the divisor back to A. So you get your actual dividend stored in A, because you have to continue with the dividing the mantissa part. So in that case, your A should contain the actual value of the dividend. So for that, you are restoring the value back into the A register. Similarly, if E contains 1, which means A is greater than or equal to B. In this case, when this situation is satisfied, we mean to say that there is a divide overflow situation. In this, so we have to first restore the dividend back, so that we perform A implies A plus B. So we are adding the divisor back to the dividend to, so that A contains the actual dividend stored. And to to overcome this divide overflow, we are performing a shift right on the contents of the dividend which is stored in A, and increment the exponent by 1, so that your dividend alignment of your dividend is done. The next step is subtracting the exponent part of your data. So your A, small a contains the exponent of your dividend, small b contains the exponent of your divisor. So you are performing A minus B. So which is done by A plus B complement plus 1. So whatever is the result that is stored in small a, this becomes the exponent of your quotient. Whatever is in A, that is assigned to B. So the next step is divide the magnitude of the mantissas. So for dividing the magnitude of the mantissa part of your floating point numbers, you are going to implement sign magnitude division algorithm. So this is the sign magnitude division algorithm. So you are just going to perform the divide magnitude part of this algorithm to divide the mantissas of your floating point numbers. Once your division is done, your quotient will be stored in a capital Q and the remainder will be stored in capital A. So whatever is stored in capital Q, the quotient, that becomes the quotient of your floating point division algorithm, which is stored in a QR, that is transferred into QR according to this flowchart. So the quotient is in QR. So this is about floating point division algorithm. Thank you.